Hello everyone, Mr. Havel here. We're going to go over 3.2 and 3.3, which are properties of logs and exponential expressions. Okay, so this first one we'll kind of cruise through. You're going to, in your graphing calculator, graph both ln x and e to the x. And so if you graphed ln x, you'll notice it goes through this point 1, 0. We've got a vertical asymptote at 0. It kind of cruises along and then shoots off to the side there. Whereas e to the x, if you graph that one, you'll notice that it cuts through 0, 1, has a horizontal asymptote at 0, and kind of the same idea, kind of flat and then shoots up. Cool. So if I look at the domain of each of the functions here, so we'll do e to the x first. This one, our domain is going to be, it goes to the left and right forever, right? So it kind of shoots off to the left and the right. And so this domain would be all real numbers, or in interval notation, negative infinity to infinity. Now the range is going to go from your horizontal asymptote and up, right? Because it's positive. So it's going to go 0 to positive infinity. Whereas our ln here, if I look at the ln x, if I look at the domain, your domain is going to be from that vertical asymptote, which is 0, to all the way to the right, right? So positive infinity in that direction. Whereas your range goes up and down forever. So again, that one's going to be negative infinity to positive infinity. Okay? And so what do you notice if you check it out? The domain and the range for each one switches, right? So they switch. And so in math, when we talk about switching or changing or undoing, something like that, we notice that these guys are inverses of each other. Cool. And so to undo or get rid of, with logs and exponentials, those guys are inverses of each other. So if we notice on the graph, one big thing is that they are reflected over that y equals x line. Okay, and that line goes through 0, 0 here, and then has a slope of 1, so something like that. And that's y equals x. And so it's reflected over there, which lets us know that they're inverses as well. Another thing is if we look at their anchor points, okay, those anchor points for one of them is 1, 0, and the other is 0, 1. So the x and y coordinates switch as well, which also give you a good sign that they're inverses of each other. And our last thing that we could talk about is one of them has a vertical asymptote versus the other one has a horizontal asymptote. Okay, so kind of opposites on that. Nice. So logarithmic and exponential functions are inverses of each other. Okay, as long as they have the same base. Okay, so I can't do like 3 to the x and then log base 5. So they need to be the same exact thing that we have. So if we look at this one, both of our bases are b. Okay, so we have log base b and b to the x. The argument of the log, that's the one that's right next to the log, and so that's going to be a. That's that guy. And then the exponent here is going to be x. Okay. And so if you notice when we deal with logs, what log is looking for that exponent. So it's looking for that. So if you notice, the log is equal to x right there, because the log is looking for that exponent. That's what it's trying to find. Now when we convert these equations to logarithmic form, there's a few different ways you can go about this. Okay, so one of the ways is just kind of look and notice where everything goes. So the base of the log is always going to be the base of your exponent. Now, again, the log is trying to find, or it's trying to be equal to the exponent, so that's why there's exponents equal there. And then your argument here is the last thing. Let's see if I can click there. And that's what your exponent is equal to. Okay? And so we're able to go back and forth into these different forms, knowing where everything likes to go. Okay? So one way that I go from log to exponent is if you put one of the properties is if you put the base to both of them, these guys cancel, and so we end up with a is equal to b to the x, which you notice is the same thing as this guy, just backwards, right? So that's one way that we're going to go about that. So here's a few of the inverse properties of a log. So if we click here, look here, log base b of b, again, if the bases match, they kind of cancel each other out. And so log base b of b leaves me with this. So log base b of b to the x is actually equal to x. Same idea, but kind of opposite if the base of the exponent is b. And then to the log, again, those cancel and leave you with x again. Okay, so if they are the same bases, then same base, then they are inverses. Nice. Okay, so we're going to rewrite this with this in mind here to change from log form to exponential form and back and forth. Okay, so in my opinion, going from log to exponential is the easiest. So all we're going to do is put it to the same base here. So put it to the same base. These guys cancel, and so we have 81 is equal to x to the fourth. Now you don't have to solve for x or anything like that. This is just putting it in the form itself. So at this point we are done. Okay. Same idea for this one. This one has, whenever it's just straight up log, remember straight up log is our common log, which is log base 10. Okay, and so we're going to put this one to a base 10. Those guys cancel, so we have a is equal to 10 to the x. Nice. And then the last one, this one we know is an exponential because it has an exponent. So what I like to do is I always set up the log first and then have the base be the base, right? So the base of the exponent is the base of the log. And then really one kind of little quick shortcut is those two always switch places, okay? So again, remember the log is always looking to equal that exponent. So it wants to equal that exponent. And then your argument's the one that your exponent equals. So they kind of just switch places there. So log base 2 of x is equal to 3. Nice. Now simplify all of these guys without a calculator. So the biggest thing that you want to notice is you are looking for same bases. You want the bases to match each other. Okay. So for me, what I do is, without even really thinking too much, I have the base match. Log base 3 of 3. Right, and unfortunately I can't just change 81 to 3, but now what I'm going to do is go, okay, well 3 to what power would bring me back to 81? Well, it would be to the 4th power, 4. And so then these guys are inverses, they cancel each other out, and so we're left with that exponent. So we are left with 4. Cool. Same idea here, we're going to have log base 5 of 5. Well, it's nice in here, but remember we've got to be able to switch this radical into exponential form. And so the power that's on the number inside the radical is your numerator. And then your index on the outside is your denominator. Now this is nice because it matches already, right? We have the bases match, so those guys are gone. And so it's equal to 1/7. Cool. Now this one's a little bit tricky, right? But the idea is the same. You still want to have the bases match, so log base 1/4 of 1/4. Now, if you notice this, we're trying to get 1/4 to go back to 256, right? So if you notice that this one is a fraction and 256 is a whole number. So in order to get that 4 that's in the denominator back up to the numerator, we need a negative exponent. And then once we've done that, that becomes 4 to the positive up in the numerator, and that would be to the 4th power. Those guys cancel and give you -4 as your exponent. Nice. These next couple, these guys are very common properties that we'll see with logs, is that ln e, remember ln is just log base e. So ln e just cancel and leave you with the exponent. Now log base or log of 1 is kind of tricky, because remember this is log base 10 of 10, and so log base 10 of 10, if you will, then 10 to what power would give you 1? So remember, anything to the 0 power gives you 1. So those guys cancel and your answer is just 0. Now the next one, we want the bases to match. So we can't change the base of the log, so we just change the base of the exponent. Now here, the tricky part is, how do I go from 36 back down to 6? So one way that's kind of a nice way, this one's not too hard to think about, but what I tell my students is when you're going from a big number down to a small number, well, how would I go from the big number to the, from the small number to the big number? So what I would do is I would do 6 squared, right? It would give me 36. Well, what you could do is if you go backwards, you just flip that one over. So this would be 36 to the 1/2. So you just flip that fraction. So here this would be 36 to the 1/2, and then those guys cancel and leave you with 1/2. Nice. Now the rest are the same exact process, but if you notice, they already have different exponents. So we'll just keep the exponents up there, but we treat them exactly the same. So here, this is log base 3 of 3. 3 to the 3rd power is 27, but it's already to the x. So if you remember exponent rules, power to a power, you multiply those two, and so these cancel, and you multiply those two, and you get 3x. Cool. Same thing here. So log base 5 of 5. Well, 5 squared brings you back to 25, but it's already to the -2x. So these guys go away, and then you multiply your two exponents there, so -4x. Number 12 looks a lot harder than it really is. If you can remember ln e, just or inverses, get rid of each other, and you're just left with the exponent. Nice. Okay, number 13 is just pretty much like 6 problems in one. Okay, so what you're gonna do is I'll kind of start. If it's an easy one, then I will just put the answer, but I'll start one at a time. So this is going to be log base 3 of 3, brings me back to 27. So cancel, give me 3. Now, if you can remember, anything ln or log of 1 is a big old fat 0. Okay. This one also is really nice because this is log base 10 of 10. And so those cancel and leave you with 4. Now this one's pretty straightforward, but there's a 5 out in front. So you do 5 times. These cancel, and it's the exponent. So that's going to give you -20. This one would be negative log base 2 of 2. Now 2 to the 5th power is going to bring it back. Cancel those guys, so -5. And then e to the ln also cancels each other out, so they cancel and leave you with 6. All right, and so we combine all that. What's that? 29 minus 9, so -20 would be my final answer with all of those. Nice. Okay, so a few important values that I yeah, you must know these ones. These ones you see a bunch. So these guys cancel right here. And again, what are you looking for? The exponent. And so the exponent in this case is just 1. So ln e is just 1. Like I said earlier, ln of 1, that would come out to be 0, because anything to the 0 power, that's what we're looking for, is going to be 1. And then ln of 0, we don't like this one. This one is undefined. So that would be in this case, what our vertical asymptote, right? And so we don't actually want that value. Nice. Now, to use these actual in real life, we have a couple different interest formulas, right? So we have compounded n times a year and then compounded continuously, right? So we refer to the one on the right as PERT, and PERT, the only time we can use that is you have to see that word continuous, okay? So continuously tells me PERT. Anything else would most likely be this one over here on the left side, okay? So a few of the highlights here. A is going to be your final amount. P is your initial. What are you putting into the bank or into your investment or anything like that? 1 is 1. Both of these n's, this is the number of times compounded times compounded per year. Okay, so you'll have stuff like monthly, which would be 12, or daily, 365. One that I noticed my students get tricked up on is semi-annually. Right, so semi-annually, the n value would be 2. Okay. Cool. And now the rate, this is your rate as a decimal. And the last one we haven't talked about yet is the time. Now these are very, very similar on the right-hand side. This is going to be your final. This is going to be your initial. E is E. Make sure to use the E button on your calculator. Okay, don't put about 2.7. There's an E button. This is, again, same thing. This is the rate as decimal. And then your time. Nice. So for these next few problems, we're going to plug it in and see what we've got. Oh, it looks like, I think just one problem actually. We'll plug it in and see how to solve it, right? So if you remember a log or ln, the idea with that is to get the exponent. So the only time I really want to use a log or an ln is if my unknown is up in the exponent. If I know everything in the exponent, then I don't need to use a log, which is nice. Okay, a person wants to invest $3,000, so that's how much they're going to start with, into a savings account for 4 years. Okay, so before I can decide, do I use the equation on the left or the right, I need to find either compounded or continuous, right? So the bank has 2 options. The first option is compounds weekly. Okay. So I might move this one over a little bit. Okay, so first option. So compounded weekly. So this is, again, we did $3,000. So this is going to be 1 plus the rate over, in this case, weekly, which is 52. And the n value up here is 52 times, it says for 4 years. For 4 years there. Okay. Sweet. And oh, here's our rate right there at 5.4%. But as a decimal, it's 0.054. Okay. and then this is going to be A. Right? And so in this case, we've got the same initial amount, E, because this one says continuous for the second option, of 5%. Okay, so we have a 5% rate on this one still for 4 years. So here, again, this is what I was saying. Do we have any unknowns up in the exponent? And the answer is no, right? We know everything. And so the nice thing for these two is you just plug them into your calculator. We don't have to worry about ln's or anything like that. The other thing here is, remember, whenever there's multiple things anywhere in the numerator, denominator, exponent, you need to use parentheses. Okay, so we plug this into our calculator, and this one will come out to be 300722.89, and this guy comes out to be 3664.21. Right, and so if you were to choose which investment you would want to do, we definitely want to do option 1. It gives you more money. Woohoo! Okay, so good little check on that one. Nice. Now here's a bunch of properties that we have for logs. Okay, so if you notice, it's very similar to the idea with exponents, right? So like the product property here. So if I did something like this, x squared times x cubed, what do you do with those? Right? You actually add them. So same thing. So when I'm multiplying two different arguments within the log, I can break them apart as two individual logs and just add them. Same thing for a quotient. If I am dividing the arguments, it's actually subtraction of each individual log. The power property, right? This is this idea here for exponents, and this would be multiplication. So this one just looks a little bit different because what we do is we take that exponent, we bring it out in front and multiply it. Okay, logs are very high maintenance. If you have like a log base 2 of 7, it's very hard to change that because that's an actual number. It's a real number. So it's an actual number, so we can't like add 2 to it or something like that individually. Okay. Now, change of base. This one's not too crazy, but the base, the way I remember it, is the base of the log. That's the one that's going to come to the bottom. Okay. This argument here stays on top. Now, you can also, if you notice, you can have ln or log. Right? So it doesn't really matter here where it says log base A. We would, in this case, just use base 10 because that's our calculator, right? So our calculator would use that. So now condensing the logs, hopefully you remember this a little bit from Algebra 2 honors, but condensing the logs, you kind of, I would say, start with the power, right? So start with the power property. And then do the addition and subtraction. So the addition, anything addition ends up in your numerator. Anything subtraction is going to end up in the denominator. Cool. Now expanding is the exact opposite. We're going to do that addition and subtraction first. Okay, so addition here again is going to be, so positive if in numerator, negative if in denominator. And then once we've done that, then we use the power property to bring the powers down. Okay, so let's try a few of these. It says condense all of these. So first thing that we want to look for with condensing is moving everything into the power. So the first term doesn't have anything, but here I want to bring this up to the power. Alright, so that's the only one. I'll write it all out for this one, but then we'll kind of do a little shortcut on the next one. Now, we're going to use the quotient and not power, product property to work through these, okay? But like I said, a nice way to remember this is if the log is positive, everything's going to go on the top. If it's negative, it goes on the bottom, right? And so this first one's positive, so it goes on top. And now to condense logs with addition, we multiply. And subtraction, we divide. Now we just need to clean this up a little bit, right? So this becomes ln of 4 times 27, and then that divided by 12 is going to simplify to ln of 9. Nice, so that's the idea of all of this. So you're going to put the powers up and then condense after that. Now 16 just looks a little beefier, right? So 1/3 to all of this stuff. So my recommendation is let's kind of get rid of him, throw him up in the power, get rid of, that's it, okay? The other thing is the only time you can condense is the ln or logs have to be the same as each other, right? So I can't have an ln and then a log base 7 and a log base 5. If that's the case, they don't combine, right? So if I combine all these, I have ln of, this guy's positive, so he goes on top. The next two are negative, so they both go on the bottom. So we have an x times x squared minus 4. Now our final thing is we have that 1/3, right? So that 1/3 is still, it's multiplying each of these individual logs. So I'm going to multiply, bring this up to the power, bring this up to the power, and bring this up to the power on all of those. So my final answer would be ln of x plus 5, 2 times 1/3 would be 2/3, divided by x to the 1/3, x squared minus 4 to the 1/3. Okay. That would be your final, you can have parentheses around here if you want, just to make sure you know you're ln'ing the entire thing there. So not super pretty, but totally doable. Okay. The next one. So the first one doesn't have a number out in front. This one does, so we'll kind of get rid of that and put it to the entire thing to the 1/2. And that's it. Okay. They're all log base 2, so I can bring that log base 2. Anything that's positive is going to end up on top. Next one's negative, so that's going to be 2y to the negative 1/2. Next one's positive, so multiply it by the numerator. And the next one's negative, so multiply it by the denominator. Okay? And so what we're going to do is we'll try to clean this up a little bit. Okay? And so here, a couple things. So one thing we can do is we look for our constants. So those are our two constants right there. So 24 over 3, so we have log base 2. So 24 over 3 is going to leave me with 8. Can't really do anything with this 6x plus 1, so we'll leave that. And then here, the final thing we can do in the bottom, we do have a z, and then we have this to the 1/2. So that is actually going to be the square. We could write it a couple ways, but you can write it z and then square root of 2y all together. Again, not necessarily, oh, sorry, man, these parentheses are terrible. Not necessarily gorgeous, but it's working, right? So same idea for this next one. So put the powers up. So this guy's going to go up here, 1/2. This guy's going to go up here. They're both ln. The first one's negative, so this is going to be 16 to the 1/2 here, and then 3 squared there. Notice how I'm not putting like negative 16 or 16 to the negative 1/2. It's just that negative dictates that it goes in the denominator. Okay, so here we can kind of simplify a little bit. Ln of 9 over, now this is just the square root of 16, so that is 4. And that's as simplified as we can get it. Nice. Now number 19 here, we've got 1/3, so we're going to throw that guy up right there. We've got a 2, throw that one up. They're all ln's again, so anything positive. 5 is positive. This whole thing is positive. And the next two are negative, so we're going to have b squared c. Even though that one looked, 1/3, sorry about that. Even though that looked like there was a lot, it was actually pretty straightforward on that one. Nice. Now the next few expanding ones, these are going to be, let's change up the color. We just have to be careful to make sure that we know how many terms there are, right? So the 3 and the x are actually 2 separate terms. Same with the 5 and the y. So for me, the best way I remember it, we can do this all in one step, is anything on top is positive, log base 7. Anything in the denominator is negative. So log base 7, I'm going to switch this to a power because I know I want it in exponential form. So to the 1/4 minus, since it's in the denominator that now, minus log y of 3. Now that I expanded it, let's bring the powers down. So the only ones I need to change is that second and the fourth one. So log base 7 of 3 plus 1/4 log base 7 of x minus log base 7 of 5 minus 3 log base 7 of y. Okay. And that is totally expanded. Nice. Nice. So 21, same idea. So ln of 2 plus ln of x cubed plus ln of y minus ln of 7 minus ln of z to the 4th. So took each individual term, positive on top, negative on bottom. ln of 2 plus 3 ln of x, bring the powers down. ln y minus ln 7 ln 7, bring this power down, so minus 4 ln z. Now again, be careful, if possible, you want to simplify. So one thing that's possible is like if you have like an ln e or something like that. Nice. Our last one here is just kind of a long one. We're going to have log 7 plus log a plus log b to the 4th minus log c plus d to the 5th. So we can group those together because they're in the parentheses. Okay, so we wouldn't see c plus d by itself in the denominator, but you could see c times d, right? So, but since we have those parentheses, they go together. So now we just have to rewrite it by bringing the powers down. And that's it, folks. Nice. Now, the last couple that we have here for 3.2, 3.3 is change a base and then give the approximate solution. So these ones are really nice because not too crazy, right? So remember, if we rewrite this, the base of the log is going to kind of be the one in the denominator. Think about it kind of denominator as the base. So we're just going to do log of 8 over log of 5. Now this is your exact solution. Now if we plug this into your calculator, just hit log of 8, close parentheses, log of 5, close parentheses. That should come out to be something like 1.292. And that right there is your approximate. Okay, so that's exact and approximate solutions. Same thing here. This is going to be log of 14 over log of 8. This one's a hard one to give partial credit on, because if you switch them, not much I can do for you on there. Okay, so that would again be your exact, and this would be your approximate. Nice. I hope you enjoyed it. Tell a friend.